This is a lecture in a series of lectures covering first order circuits, and this is, I think, the 7th pencast. And in this little pencast we're going to look at the situation where you're driving a circuit, in this case an RL circuit, with the voltage source, but the voltage source is going to be connected to the network through a switch. And that switch, yes, will open at some time. We'll say it'll open at time t0. And we have we'll say it's a 10 volt source, Vs. And we have an inductor, L. We have a resistor, R1, and a resistor, R2. And we'll have IL. And we'll say we have a current I1. Okay, current I1. And what we want to do is find IL of t and I1 of t. Okay, so what we need to do, we're not told the initial condition on this inductor. We are just told that the switch has been closed for time infinity past, and at time 0 it opens up. So let's pick some values here. Let's say that the inductor is 2 Henry, and let's say that this is a 1 ohm resistor, and this is a 3 ohm resistor, and we have a 10 volt source. So what we want to do is consider the circuit prior to time t0 when the switch opens, and then consider the circuit after time t0 when the switch is closed. So prior to time t0, the switch is closed. So what we have is the voltage source Vs, and we are connecting that across the 1 ohm resistor and connecting that across the series connection of the inductor and the 3 ohm resistor. Now, if this has been the situation for all time infinity past, we can assume that the inductor current is in steady state. So we would say that DIL dt is equal to 0. Okay, this is since this circuit has been driven by Vs, which is constant, for infinite time, from minus infinity to time 0. Okay, so therefore, if DIL dt is equal to 0, then VL is equal to 0. And then we can write that IL is simply equal to Vs divided by 3 ohms. Okay, so that'll be 10/3 of an amp is what will be flowing through IL. So we'll say IL of t is going to be equal to 10/3 of an amp for all t less than 0, and we don't know yet what it is for time greater than 0. We can also write an expression for I1. Okay, I1 is the current going through the 1 ohm resistor. And notice it does not depend at all on what's going on with the inductor, because it has applied across it the voltage source Vs. So it'll be Vs over 1 ohm, which would be equal to 10 amps. Okay, so here we can write I1 of t is equal to 10 amps for t less than 0, but we don't know yet what it is for t greater than 0. So that circuit with the switch closed helped us find the initial condition for the inductor current and the initial condition or the initial current for it flowing through the resistor, the 1 ohm resistor. Now let's look at time greater than t greater than 0. The switch will now be open, so it will be out of the circuit. We won't even draw the source, and all we have is the 1 ohm in series with the 3 ohm in series with the 2 Henry. And we have IL, and we have I1, and we notice that now I1 is equal to minus IL. And this might be a new situation for you, in that you would think okay, if I1 is equal to minus IL, is it not always equal to minus IL? I mean, we never had a circuit before where at one point we had this relationship between two branch currents, and now it changes. Well, the reason that it changes here is we've literally rewired the circuit. So before time 0, this switch was closed. This voltage source was wired into the circuit. At time 0, we unwire that. We disconnect the source. And so we're actually solving a different circuit. And so that's why we can say now that I1 is equal to minus IL, but when time was less than 0, we couldn't say that I1 was equal to minus IL. Well, this is a trivial circuit at this point. We have an R equivalent that's going to be equal to 1 plus 3, or 4 ohms. And so now we can write that the time constant, which is equal to L over R, is just equal to 2 Henry over 4 ohms, or 1/2 second. Okay, and we can write the total response of the current, which is just a homogeneous response because there is no driving force. So we can say IL of t is equal to ILH, homogeneous response. And this is equal to IL at time 0 minus, which is actually equal to IL of 0. IL of 0 because current in the inductor can't change in 0 time, times e to the minus t over tau. And we'd say, rewriting that, IL then is equal to 10/3 of an amp, 10/3 of an amp times e to the minus t over 1/2 second. Okay, I should say just minus e to the minus 2t. Okay, and now we have I1 then is equal to minus 10/3 amps e to the minus 2t. Okay, so finally now we can write the complete solution for IL. We can write that before time 0, it's 10/3 of an amp for t less than 0, and it is 10/3 times e to the minus 2t for time greater than or equal to 0. And we can say that I1 is equal to 10 amps for t less than 0, and for time greater than 0, it is minus 10/3 of an amp e to the minus 2t. Okay, let's plot that. Let's see here. Okay. So if this was 10 amps up here, then this might be 10/3 of an amp, and this might be minus 10/3 of an amp. Okay, so the inductor current starts out at 10/3, and up until time 0, it's going to be, I did that wrong. Inductor current's right here, starts out at 10/3. So this here is IL. Okay, and then at time 0, it's going to start dropping and exponentially decay down to 0. Okay, this is IL of t. I1 is up here. That's the one. I1 is 10 amps up until time 0, and then it actually switches and goes to minus 10/3, and then exponentially decays. Okay, so the I1 actually does this kind of thing. Right. If we look at the circuit, we can see why. So if we go back up, take this and go back up to this circuit, notice that initially when the switch is closed, the current through I1, through the 1 ohm resistor, is purely dependent or purely determined by just the 10 volt source. It's 10 volts over 1 ohm. Right? But at the same time that the VS source is supplying that 10 amps to R1, it is also supplying current through the inductor. And that current we found to be 10 volts over 3 ohms, or 10/3 of an amp. Now when you open the switch, the current source for I1 coming from VS goes away. And now the only current that is going to flow through I1, through R1, is the current that is circulating through IL, through the inductor. the circulating current IL flowing through the inductor. And since it's flowing clockwise, it's going to flow back up through R1 in a direction opposite to I1. So an important point here is to think about what currents or voltages can change in zero time and which ones cannot. And the thing to remember is that if a current corresponds to a particular energy state, which it does here, the current through the inductor corresponds or is related to the energy in the inductor, it cannot change in zero time. That's just like saying the velocity of some mass cannot change in zero time, because if it could change in zero time, it would mean you'd have to be able to deliver infinite power to it. So here you can kind of critique your answer to the extent of, or at least in the context of looking at whether there is an appropriate discontinuity in current or not. You should never see a discontinuity in current through an inductor. Okay? Now it turns out you can have a discontinuity in voltage. We didn't plot the voltage here, but there's definitely a discontinuity in voltage across the inductor. And that's okay, because voltage across an inductor does not map to the energy storage. That's like saying the force applied to a mass is not directly related to the energy in that mass. The kinetic energy of the mass is 1/2 mv squared, right? Now changing the force will, over time, integrating, will eventually change the velocity and change the energy that is stored, but not immediately. Now, regarding I1, we see here that I1 changes in zero time. And if that's troubling you, the thing to remember is that the current I1 does not correspond to current flowing through an energy storage element. We haven't violated any finite power requirement here by saying if current changes in zero time, therefore we must have delivered infinite power to get this current to change. It's not the current through an inductor that has changed in zero time. It's the current through the switch, and the reason that it's changed in zero time is because the switch opened in zero time. Of course, this is not a practical situation. No physical switch can open in zero time, but it can open, quite rapidly. And for our purposes here, we're going to treat the switch as truly opening in zero time because we're doing, paper exercises at this point.